Lesson 11 is transformations of log functions, and they're going to work the same way as transformations on any type of function. A is that letter that we use to represent a vertical dilation and a reflection over the x-axis. That's going to be a number multiplied out in front of the log. If the absolute value of A is greater than 1, that would be a stretch. If it's between 0 and 1, it would be a compression or a vertical shrink. And if A is negative, that would be a reflection over the x-axis. B is that number that's like in the 1 over B times x, kind of inside the argument that's inside parentheses in this case when we are taking a log. B tells us horizontal dilation and if there's a reflection over the y. Keep in mind in whatever number is in the function itself, because this is a 1 over B, B is going to be like the reciprocal of what we see. If B itself is greater than 1, that would be a stretch. If it's between 0 and 1, it would be a compression. If it's if it's negative, it would be a reflection. H is the letter we use for horizontal translation, that is moving something side to side without changing the shape or the orientation. That's something that is being added or subtracted from x inside parentheses. And then K is our vertical translation, so moving the graph up or down, moving the function up or down without changing the shape or orientation as well. And that's going to be just a constant added on to the end. Okay, so example 1, describe the transformation from f of x to g of x. So for A, f of x is log base 2 of x minus 3, and then g of x is log base 2 of x plus 1. So we have to look at what change is happening and where is it happening. So you could see in the function we're going from negative 3 to a positive 1, and those are both constants that are added to the end of the function. They are not in parentheses with the x, so that means that these are like k values that are changing that number that's added to the end. So we're going from what once was a minus 3 to now a plus 1. So to go from a minus 3 to a plus 1, we would have to add 4. And that would mean that k is positive 4. So this would be a translation up 4 units. So k was 4. Again, it was k because it was a number that was being added or subtracted to the log, and it wasn't in parentheses. So if it's not in parentheses, it would be k, and then k indicates a vertical translation. Since we're going up by 4, it'd be a translation of 4. And then for B, f of x equals log base 1/3 of x. G of x is log base 1/3 of negative 4x. So we'll look to see where the change is happening and what that change is. We're starting with just a log of x in f of x, and then it's changing into log of negative 4x. So this was once like a 1x essentially, because there's no number there, and it's changing to a negative 4. Since this started with just a regular x, I would it is essentially like a parent function for log base 1/3 of x. So we really just have to look at, okay, what is that negative 4? So it's being multiplied by the x inside the parentheses, so it's definitely a b. But remember that b is going to be the reciprocal of whatever we see in the function. So the reciprocal of negative 4 would be negative 1/4. And if b is negative 1/4, that means two things. The negative means that there's going to be a reflection. The 1/4 means there's going to be a compression, a shrink, because that number is between 0 and 1. And again, whatever we see in the function, I know we see negative 4. B is the reciprocal of what you see because we have 1 over b in the formula itself. So this would be a reflection. And since it's b that's changing, it's a horizontal reflection, so it would be a reflection over the y-axis. So that's for the negative. And then the 1/4 aspect of it is a horizontal compression. So we're looking at this guy right here. So b is between 0 and 1, so it'd be a horizontal compression. Okay, so I'm just going to shorten compression down to compress, but there's two transformations happening here. Again, a reflection over the y-axis, that's the negative aspect of it, and then the 1/4 gives us a horizontal compression by 1/4. And it's horizontal because it's that b value that's changing. It's the number that's inside the parentheses with the x, so it's going to be a horizontal dilation. Okay, so example 2, apply the described transformation, to f of x to get g of x. So A is f of x equals log base 5 of x. That's where we're starting. F of x is oh, that's a typo, that's why. F of x is translated. I'll fix it by the time the principal one is posted. F of x is translated 3 units left and 7 units down to get g of x. So if we're going 3 left, that's going to be our like horizontal translation. And then 7 down is our vertical translation. So this would be like h equals -3, since like left would be negative as far as left or right. And then if we're going 7 down, that would be k equals -7. Okay, so for this problem, we just have translations, meaning we just have an h and a k. We don't have to deal with a and b. So sometimes something that's helpful is to kind of take this formula up here and just like take it down to our problem, but only really include the placement for the letters that you need, meaning we just need h and we just need k, so I'm only going to include those. I'm not going to worry about a and b. So this will be g of x equals... the original log was log base 5 of x. So that's a parent function for a log with a base of 5. And then, but I need to put something in for h and k. So I'm going to put in an x minus h here. And then plus k. And then now I can kind of see where each of my values need to go. So I'm going to... h is -3, so I'm just going to go ahead and take out the like h and put in a -3. So we'll take out the h, put a -3 in there, since we're supposed to go left 3. And then k is supposed to be -7 because I'm going down 7, so I'm going to take out the k and put a -7 there. And then now we would just want to simplify, so like no leaving like kind of double symbols in there. So it'd be g of x equals log base 5 of x minus -3. Double negative turns to plus, so this would be x plus 3. And then plus -7 we would just rewrite as -7. So g of x equals log base 5 of x plus 3 minus 7. That means we started at log base 5 of x and we translated it 3 left and 7 down. Okay, for b, f of x equals log base 1/2 of x. F of x is reflected vertically and stretched vertically by a factor of 4. So if you have like a vertical reflection and a vertical stretch, those really kind of all go into the same letter. I'm going to go back up here really quick. So vertical stretch would fall under vertical dilation, and then vertical dilation and reflection go together. Those are both A. So if we have a reflection and a stretch by a factor of 4, all that together means A equals -4. So negative for the reflection and then 4 for the stretch by a factor of 4. So I'm going to kind of do the same thing here. I'm going to look at where A goes in this formula. It's a number that is being multiplied out in front of the log. So that means that I have to take my A equals -4 and I need to multiply it out in front of my like original log to get g of x. So it'd be g of x equals, I'm going to put the -4 out in front right here. So -4 and then times all of my original function just stays exactly the same after that because there's no other changes. So it'd be times log base 1/2 of x. So g of x equals -4 times log base 1/2 of x. So whenever you have a vertical dilation or a reflection, it's just a number that gets multiplied out in front of the function. The negative from the -4 is for the reflection, the 4 is for the stretch. Moving down to example 3, it says write a transformation rule and a function rule for g of x. F of x is log base 5 of x and plus 1, and we need to figure out what the transformation is based on the movement in the graph. So f of x is the blue line, g of x is the red line. We need to figure out how we get from f of x to g of x. So the kind of orientation or the shape of the graph is not changing at all, so that's kind of indicative that it is just a translation. So to figure out the translation, we have to focus in on a couple key points and see how they move. So for example, one of the points that pops out to me is this point right here, 1, 1 on f of x, and then it looks like that same point kind of right around the corner, I guess, on g of x, just a little bit to the upper right of where the graph kind of bends. And then as far as the transformations to get from one point to the next, we are going up 3. So the vertical change would be 3. And then we're going to the right 2. So the horizontal change would be 2. So if there's no stretch or anything like that, we just have to worry about h and k for our transformations. So remember, h is the horizontal change or translation. So h is going to be 2, and then k is the vertical translation. So k would be 3, how far up or down we're moving. So since I just have translations, I'm going to write a transformation rule with just h and k in it. So it'd be g of x equals, and this is not really involving the log quite yet, so it's just going to be in reference to f of x. It'd be g of x equals f of x minus h, because we have h is going inside the parentheses with the x, and then plus k. And again, h is the horizontal difference or movement. So in this case, h would be 2, and then k is the vertical shift as well. Okay, so in my function rule, I'm just going to go ahead and take out h and k and put in the actual values for them. So we're going 2 to the right, so h would be 2, so I'm going to put a 2 in here. And then we're going 3 up, so I'm going to put in a 3 for k. So it'd be plus 3. And what this is reading as is g of x equals f of x minus 2 plus 3. That means that g of x is f of x translated right 2 and up 3. So to get from our blue line to our red line, we have to go right 2 and then up 3, or vice versa. The order doesn't really matter with the translations. But this is going to be our transformation rule. So just writing what the transformations are into f of x and not really worrying so much about what the original function is yet. And then now to get my actual function rule, it means that we have to actually put these transformations into our original function. So it'd be g of x equals, we're going to start with log base 5, and then f of x minus 2 means that wherever there was an x in the original function, it'll get replaced with x minus 2. So actually, I'm going to write out the original function first and then kind of show the replacement after. So the original function was log base 5 of x and then plus 1. So wherever there's an x in the function, it would get replaced with x minus 2 because that's my new argument, that's my new input. So it would be log base 5 of x minus 2, and then that plus 3 at the end means that 3 just gets added to the end of f of x, so it would be in addition to that 1 that's already there, and of course we'd want to simplify. So it'd be g of x equals log base 5 of x minus 2, and then we would add these two together to get plus 4 at the end. So then now this whole thing, the g of x equals log base 5 of x minus 2 plus 4, that's the actual function rule for g of x with the transformations put in. So on the exam, it'll kind of ask you to write a both the transformation rule and the function rule. So just kind of knowing how to put it in just, I guess, function notation before you actually like write the new function is important to know how to do both.